on TVR's 70th birthday. So I've enjoyed many discussions with TVR over the years. Since I was kind of a struggling PhD student, look at interesting physics problems like we heard yesterday, but always trying to maintain some connection with experiments. Okay, so hopefully this talk will try to do some of that. I'll try to tell you about some new physics that we expect when you combine spin-orbit interactions with electronic correlations. And of course, that's a rather general topic. I'll focus on two examples. One will be what we call the Weyl semimetal, some unusual properties which we associate with that, and how it may be realized. So that's in this paper. There's a very nice viewpoint written on our paper by Leon Balens, and that's probably the best place to look for a quick summary. And also with some more recent work on transport in these phases. And hopefully, if I have time, I will talk about a rather different phase, but also within this ambit of the interaction, the novel things that appear when you have strong spin orbit. In this context, when the spin orbit occurs in a Mott insulator, we'll see that unusual types of superconductivity can be induced, and we propose that this may be realized in a particular material. And these are my collaborators. Several of them are or were at Berkeley, but we also collaborated with some ab initio experts, Sergei Savrasov and Shangang Wan, so we could try to connect some of our ideas to real materials. Okay, so Zaid gave a very nice introduction to topological insulators, and in fact my talk is not really about topological insulators, but it will be inspired by many ideas that have come up in the context of topological insulators. Okay, so I won't really try to give you an introduction. I'll simply emphasize a few physical points, just select a few of them, which will sort of make an appearance in some different disguise in the material that I'll talk about. Okay, so we all know that these topological insulators, topological band insulators, they're pretty conventional insulators if you sit inside the bulk. Okay, so if you have some microorganism sitting inside the bulk of a topological insulator, it will be very hard for you to tell whether this is a topological insulator or a trivial insulator. The unusual physics appears when you go to the surface. Okay, and that's one way to expose the unusual physics. You have exotic surface states, and the ingredients that are required for these Z2 topological insulators is you need strong spin-orbit interactions, and you need time reversal symmetry to define these phases precisely. Okay, and the unusual surface states, for example, these three-dimensional topological insulators, the surface states are unlike anything you would see in a purely two-dimensional system. For example, you have a single Dirac point on this, the surface of this three-dimensional insulator. It's impossible to get a single Dirac point in a purely two-dimensional system if you have time reversal symmetry. Field, for example, has got a pair of these Dirac points. Okay, so that already tells you that there's something unusual. You get something, although the surface is two-dimensional, you get something that's impossible for a purely two-dimensional system to do. Okay, so a poor man's way of thinking about the band topology is that you start with the conventional insulator and you do a band inversion. Okay, invert the conduction and valence bands. You can make this more precise if you have inversion symmetry. Okay, inversion symmetry is not required to define these phases, but it's convenient. If you have inversion symmetry, you can label these states by their parity under inversion, and then these states can go through each other. Okay, and these states, for example, at this high symmetry gamma point, they're Kramer's pairs. Okay, and so a pair of levels pass through each other with opposite parity. That takes you from a trivial to a topological phase. Okay, and so people have classified not just these Z2 spin-orbit topological insulators. There's now a complete classification that applies to non-interacting fermions, and this classification can be in any dimension. And this column over here tells you the kind of symmetry that we're going to associate with our set of non-interacting fermions. Okay, so let me blank out the dimensions we're not interested in. Let's just look at 1, 2, 3 dimensions. Surprisingly, we'll actually use the 4-dimensional column of this table later in this talk, but we'll see how that comes about. So to give you some pointers of some familiar faces in this table, this row over here is the quantum Hall effect. There are non-trivial insulators in 2 dimensions. And this one is the Z2 topological insulators. There's a non-trivial insulator both in 2 and 3 dimensions. And the others are typically thought of as superconductors. They're again gap phases which can be modeled by non-interacting fermions and which are stable to disorder. Okay, so that the introduction of disorder actually simplifies life. It gives you a very simple, a finite set of different cases to look at. And when you also say that there are gap phases, you can classify them all, assuming that there are no interactions between the fermions. And at least for this context, the kind of materials that in which these topological insulators have been realized so far. So this one was the first topological insulator discovered, pioneered by Zahid and his group, and subsequently many others were discovered. All of these are S and P band materials. You expect weak correlations. Okay, so an obvious question is what happens when we combine electronic correlations with this kind of topological physics. Okay, so first of all, where would you look in terms of materials for such physics? You want to combine spin orbits with electron correlations. So obviously to get larger spin orbit, you want to increase the atomic number of your elements. So you go down the periodic table. And if you also want correlation effects, you're best off looking at these transition metal systems. So at least we'll focus on these 5D transition metal compounds. Okay, so that will give us some guidance where to look for interesting physics which combines spin orbit and electronic correlations. Okay, so one very simple consequence of electronic correlations is that you get magnetism. Okay, so what we'll first ask is what happens when I introduce magnetism and ask about possible topological phases. Okay, so of course you have broken time reversal symmetry as soon as you introduce magnetism. So the Z2 classification previously is not relevant, and the question is are there other ways of classifying phases in the absence of time reversal symmetry? Okay, so we can do exactly what we saw before. Let me imagine that I have some magnetic system and attempt to make a band inversion. Okay, so start with a magnetic insulator that's trivial and try to invert the bands. Okay, to sort of copy what was done in the context of these Z2 topological insulators. Okay, so of course to make this band inversion precise, I need inversion symmetry. So let me retain inversion symmetry, and I have these 2 bands which are labeled by different parity eigenvalues. At least the states over here are labeled by different eigenvalues under inversion. So what happens when I take these states through each other? Okay, so when you, in the absence of time reversal symmetry, these are non-degenerate states. Okay, so they're not Kramer's pairs, they're just individual states. And what happens when you take them through each other? So what you can prove is that it's impossible to get an insulator when you do this band inversion. Okay, so if you have non-degenerate states with opposite parity, you take them through each other. This is actually not an insulator. The energy gap must close somewhere in the Brillouin zone, and typically it closes at points in the Brillouin zone. Okay, and if you look at the electronic dispersion in the vicinity of these points, these are the electronic dispersion looks a lot like the Weyl equation. I'll talk about that in a minute. So we call these Weyl points because of that similarity. Okay, so let me remind you what the Weyl equation is. So we all know what the Dirac equation is. The Dirac equation is an equation for electrons and positrons in 3 dimensions, and it has these 4x4 matrices that end up giving you this linear dependence on the momentum and a possible mass term. Okay, so it's a 4-component wave function. What Weyl noticed is that you can actually simplify this equation. You can actually write it as a 2x2 matrix equation, but the difference is that once you do that, these Dirac matrices simply become Pauli matrices, okay, 2x2 matrices. And since there's no 4th Pauli matrix that anticommutes with all of this, you can't really give this particle a mass. Okay, so these Weyl particles are always massless, and it was believed the neutrino was a Weyl fermion until people discovered that the neutrino has a small mass. Okay, so the Weyl equation always describes massless particles, which is sort of half of the Dirac equation. Okay, it only has half as many components.
So if you take Dirac particles and make them mass zero, what will happen?
You will get two sets of Weyl particles. Yeah. So it breaks up into a pair of Weyl particles. But generically, that's fine-tuning, right? You have to fine-tune to get mass zero. In this Weyl equation, it's automatically mass zero. Okay, so what happens when you do this band inversion is that in fact there are at least 2 points in the Bilwa zone where the bands touch and you get a semi-metal. Okay, so it's not a true insulator, it's a semi-metal. In fact, it's a very close analog of graphene, but in 3 dimensions. Okay, so what you can easily show is that these Weyl points, these band touchings, must come in pairs. Okay, so if you have one band touching here, described by this Weyl equation, there must be another one which is described by the opposite chirality or the opposite locking between the spin and the momentum somewhere else in the Bilwa zone, okay, for consistency.
Sorry.
Yeah.
In the case of Dirac, you had particles and holes, or electron, positron, and then 2 spins. What are the things in Weyl? Do you also have particles and holes and also 2 spins?
Okay, so I'll be a little careful what you mean by spin. But essentially, if you take this pair, this Weyl point and that Weyl point taken together, that's like the massless Dirac theory. So there are half as many degrees of freedom in a single Weyl point. So if you like, you can say that there are electrons and holes. There's a charge associated with them. So unlike Majorana fermions where there's no charge, so there are 2 ways of taking half the Dirac equation. One way is this Weyl procedure where you have these gapless excitations which are both particles and antiparticles, but a single branch of them. The other way is the Majorana way of taking half the Dirac equation where there's no charge conservation, and that will be typically gapped in 3 dimensions. That's like a superconductor analog of this.
So the physical spin doesn't survive.
Yeah, if you like, the sigma is the physical spin, or it transforms in the same way as the physical spin. So if you like, you can say that there's spin momentum locking, just like what Zaid was showing in the circle of the 2-dimensional insulator, but here it's like a hedgehog in 3 dimensions. And there's the opposite texture in the other one, yeah.
So if I want this plus one, then the momentum is spin like this.
Yes.
And the other one is momentum is spin.
Yes, yeah. That's the simplest case. In general, it's you can define a Chern number when you take this surface, and that'll have Chern number 1. That's the more general way of defining it. Okay, so they always come in pairs, and what's important over here is that these are non-degenerate bands. Okay, so you must break either time reversal or inversion symmetry in order to get non-degenerate bands. So here we have chosen to break time reversal symmetry. And it appears that there's something topological about this. You look at this texture, it looks like a hedgehog. It seems to have some topological feature in the sense it always comes in pairs. So you can ask, is it possible to define topology, band topology, not just for insulators, we already seen how that's done for insulators, but for a semi-metal. Okay, something where the band gap doesn't close, where the band gap is not open everywhere in the Bilwa zone, you get these touchings of the band. Okay, so I won't do that in a very precise way. It is possible to extend these topological ideas to semi-metals, but let me give you a sort of a heuristic idea how you could try to do this. Okay, there are a couple of different ways, but let me give you some idea. So the key, it turns out, is that you need to appeal to momentum conservation. Okay, so unlike topological insulators where you can define them in the absence of translation symmetry, you can define them, in fact, in the presence of disorder, here we will need to assume that crystal momentum is conserved. Okay, or at least we'll make that assumption. Crystal momentum is conserved, so I can talk about a part of the Bilwa zone or a particular point in the Bilwa zone. Okay, so you can think of graphene in a way as a topological semi-metal. Okay, so if you look at graphene, if you go to just one of the 2 Dirac points, zoom in on one point in the Bilwa zone, this looks like the surface state of a 3-dimensional topological insulator. Right? So if you're allowed to make this distinction, if you're allowed to go and look at one of them, you can make this connection to the surface state of a topological insulator in one higher dimension. Okay, so by this analogy, you could ask, how do I define a topological semi-metal in 3 dimensions? And obviously what this suggests is look at four-dimensional topological insulators, look at the surface states, and if you can find such a similar dispersion at some point in the Brillouin zone of your three, call this approximately over here, but over here I can remove that word approximately. If you zoom in on one of them, it is really the surface state of a four-dimensional topological insulator. Okay, so that may be nice, that you associate the word topological with semi-metal, but what is the consequence, right? Is there any physical consequence of this? So what we have learned from all of these topological phases is that if you want to expose their topology, you should go to the surface. Okay, so what are the surface states associated with the Weyl semi-metal? Okay, so let's try to look at the surface states. And there's one thing that we need to understand over here, how to define surface states for something that's not a true insulator. Okay, if you have a true insulator, if your energy is inside the band gap, then the surface states are defined everywhere in the surface Brillouin zone. Okay, if you put a particle at any momentum in the surface Brillouin zone, it cannot escape into the bulk at that particular energy. Okay, but if you have a bulk that's gapless, then you have to be a little more careful. You can define surface states, let's say you pick zero energy, which is the energy at which these Weyl points are at, the chemical potential at which they're at. At that particular energy, you can define surface states anywhere in the surface Brillouin zone, except at 2 points, which is the projection of these points onto the surface Brillouin zone. Okay, at those 2 points, if you put on an electron, they can leak into the bulk, so surface states may not be well defined. Okay, so that's the surface Brillouin zone. And it turns out that the surface states that you get, defined everywhere else in the surface Brillouin zone, takes the form of a Fermi arc. Okay, so you have low energy or zero energy electronic excitations at the surface on a line that connects these 2 points. Okay, so we're used to, we generally expect Fermi surfaces to be closed surfaces, and that's definitely true in any two-dimensional band structure. Okay? So what people call open Fermi surfaces is also a closed curve. You can have an open Fermi surface which goes from this point to the identical point over here. Because these are identified, that's also a closed loop. In 2 dimensions, you can never get something that looks like that. Okay, you never get an arc, at least in a weakly interacting system, you can never get this kind of an arc kind of Fermi surface. Okay, but it turns out that you can realize it as the surface state of a 3-dimensional system. Okay, but the 3-dimensional system is not an insulator, it's actually a semi-metal where the concept of surface states loses its meaning at these 2 points, the ends of the Fermi arc. Okay, so that seems a little disturbing. You can, maybe some of these observations will make you feel better. So let's say you take a slab and you look at both the top and the bottom surface. So this is a surface state of excitations that live on the top surface. What are the excitations that live on the bottom surface? Okay, so it turns out that's also an arc, but taken together, these 2 arcs form a closed Fermi surface. Okay, so if you view this 3-dimensional system as a slab, which is effectively 3-dimensional, then you get back what you expect, you get a closed Fermi surface. Okay, but as you make the thickness of the slab larger and larger, these states end up living at opposite sides of the sample. Okay, so very similar to topological insulators, the surfaces give you some dispersion that you can never get in a 2-dimensional system. Nature of the dispersion is different, it's actually a Fermi arc. Okay, so I've shown you the excitations that live at a particular energy. We can ask what the dispersion is. What does this look like if I plot it as a function of energy? Okay, so that's the energy along the 3rd axis. And these states, these cones are actually bulk states. And this purple over here is the surface state. If you section this at a particular energy, for example, zero energy, exactly at these Fermi points, you get the Fermi arc surface state, and just 2 points for the bulk states. If you move up in energy, you actually end up getting little disks. This point opens up in a little disk where the surface states are no longer defined, but this arc still persists, connecting those disks. So there's a sort of velocity associated with this Fermi surface. It's a chiral excitation, the electrons move in a particular direction. Okay, so people have talked about Fermi arcs before in a phenomenological context, in the context of Cook rates, where it's not very clear how they emerge, and I doubt it has anything to do with this particular mechanism. But this gives you a concrete microscopic model where you can realize these Fermi arc states. Okay, but they're surface states. That's the the price you pay for getting it in a weakly interacting system. Okay, so let me quickly prove why you get these Fermi arc states. So it really has to do with the fact that these Weyl points are sources of churn flux. Okay, so there are sort of sources and sinks of churn flux. So if you look at a two-dimensional section of this three-dimensional Brouillard zone, these planes, you can define a churn number on them. Okay, and let's say this plane has churn number 0. If I take another plane in this three-dimensional Brouillard zone, which is on the other side of this Weyl point, taken together, these two surfaces should accommodate a net churn number of 1, okay, to accommodate the sink of churn number inside. Okay, so it turns out that if this is 0, this had better be 1. So all of the planes that live in between these two Weyl points have churn number 1. Okay, and then you go back to churn number 0 when you exit the other Weyl point. Okay, so if you have a churn number 1 band structure, that's essentially a quantum Hall band structure. It will have surface states. It will have a chiral edge state. So this plane will have a chiral edge state. So if you section the chiral edge state at any energy, you'll find that there's a point where it intersects. Okay, generically just one point. You keep doing that for all the momenta that live between these Weyl points, you'll end up getting this arc. Okay, so this arc is really the locus of these intersections as you move between these Weyl points. Okay, so that's a quick proof of why these Weyl points have to appear just from the band topology. Yeah. For the simple Weyl point, it is because it's a single, it's like a monopole. So if you have a Hamiltonian that's P dot sigma, you can calculate the churn number, it's one winding. Yeah, you can think of like a double Weyl point. In fact, I'll tell you a candidate material which we believe has a double Weyl point, churn number 2. In which case you'll get two of these edge states. Okay, so that was sort of a scenario. Question is what material might be in this phase. Sort of a favorite system to look at for people who want to combine correlations and spin orbit are these Iridium Oxides. One reason is that the electronic structure is very simple. If you just look at one iridium ion, in the typical octahedral oxygen environment, it has one electron in a pair of levels. Okay, so it looks a lot like the Hubbard model, the superband Hubbard model, spin up and spin down per site, except that these are not really spin up and spin down states. Okay, there are some strongly hybridized states between spin and orbital angular momentum, so it's total angular momentum equal to half. Okay, when you organize these iridium ions into a lattice, you essentially have something like a single band Hubbard model, and that gives you some good intuition where to look and so on. Okay, so which lattice would we like to look at? So I'll talk mainly about iridium in this Pyrochlore lattice, corner-sharing tetrahedron, realized by this class of compounds. A can be one of many different elements, typically rare earth, but it could also be yttrium. And you have these ions at the sides of the Pyrochlore lattice. Okay, so this is an interesting structure as pointed out by Preston and Balance to look for topological phases. Okay, so we followed their suggestion. Our conclusion is actually different from theirs. We got a different phase, but I think the general idea, this is a good lattice to look for topological phases, turned out to be correct. Okay, if I have time, I'll also talk about the honeycomb lattice of iridium ions realized in these compounds. And there's a very interesting suggestion that this could be close to something called a Kitaev spin liquid Hamiltonian. Okay, and let's see if I have time. Okay, so coming back to these Pyrochlore Iridates, so we collaborated with these ab initio people who did LDA plus spin orbit plus U calculations to try to figure out what might be the ground state of iridium arranged in this lattice. Can you have a parameter in your hand, this U, that summarizes the electronic, the strength of electronic correlations on the iridium ions? Okay, so the first thing that was found is that this is always magnetically ordered. Okay, and it's an interesting question to ask, what is the natural magnetic order on the Pyrochlore lattice, very frustrated lattice. It turns out the spin orbit actually lifts that frustration, and you end up getting this all-in, all-out magnetic order. Okay, all of the spins point in to the center of the tetrahedron, or all of them point out. Okay, so that turned out to be the magnetic order we found. But what about the electronic structure? So that really depends on what this U is. Okay, if this U is small, you end up getting a metal. If you use very large, you get an insulator. You can roughly think of that as a Mott insulator, 1 electron per site, where the electronic spin points in the direction as shown over here. Okay, but really what you're interested in for these 5Ds is some intermediate U, and the question is what happens there. Okay, what you find is this is what the electronic structure looks like along high symmetry directions. Fermi energy is here. So naively, if you look at it, it looks insulating. Okay, but I told you before that there's a parity criterion that can allow you to diagnose if something is insulating or not. In particular, it tells you that in certain cases, it cannot be insulating. In fact, if you do a parity criterion for this particular system, it turns out it predicts that there are Weyl nodes. You're not seeing them because you're looking at just along some high symmetry directions. In fact, if you go off those high symmetry directions, you find there are these points where the bands touch, these Weyl points in the band structure. Okay, now because of the high symmetry of this particular material, it turns out that there are many of these Weyl points. There are 24 of them, in fact. But they're all at exactly the same energy, okay, because you can relate any pair of them by a symmetry.
The location of the Weyl point is not fixed?
It's not fixed, yeah. Unlike graphene where symmetry protects where it is, these can move. So in fact, one way to think about this Weyl semimetal is like it's an intermediate between a topological phase and a trivial phase. When you're making that transition, you can get an intermediate region where the Weyl points sort of traverse the Brillouin zone. They appear somewhere and then they go and annihilate somewhere else. And in the process, they change the topological index of your insulator.
In short, they can be routinely missed in electronic structure calculated.
Yeah.
Plotted.
Yeah, so this, it took us some convincing. We had this parity criteria, so we knew they had to be there somewhere. Right, but it's easy to miss them. They're just points where they touch. So, it's actually quite generic to get band touchings in 3 dimensions. But the nice thing over here is that they're all at the Fermi energy, okay, because they're all related by symmetry, and then Lagrange's theorem tells you the Fermi energy has to go through them, just like in graphene. Okay, so that was the electronic structure. So we predicted that it's a magnetic Weyl semimetal, at least for some of these values of A, some of these elements. So we can try to compare with the experiments. There are actually quite a few experiments on this class of compounds, and some of them are quite recent. So first of all, it's quite clear that these materials are magnetically ordered. So here A is actually European. You see in muon spin rotation, onset of magnetism at around 120 Kelvin. There's a more recent sort of tour-de-force neutron scattering experiment that seems to indicate it is this all-in, all-out state. Okay, so there's some evidence now, experimental evidence, that this all-in, all-out magnetic order is realized in these compounds, at least some of these compounds. Okay, so what about the electronic structure? So we can look at transport, and this is a pioneering paper by Yoshi Maino several years back. They looked at the whole family of these Pyrochlore Iridates, where the A is being changed. So depending on what this A is, this materials can either be very metallic, praseodymium is a good example, it's very metallic, or for example yttrium, it looks insulating-like. So it's not quite an insulator if you look at these resistivity values, but there's some systematics over here. By changing the ionic radius, you can actually go from metal to something that looks less and less metallic. So similarly for this europium and neodymium and so on, they all look like bad metals, and we're proposing that these bad metal conductivities might actually be related to the fact that they're Weyl semimetals. Okay, so they have a temperature dependence, and if you have a Weyl semimetal, the transport of electrons in such a state might end up giving you a resistivity profile that looks like that. Okay, so let's try to make a calculation what would resistivity look like in a Weyl semimetal. Okay, and try to compare with the experiment. Okay, so there are a number of different ways in which a current can relax. The one we usually look at is disorder. It turns out that if you just look at disorder, white noise disorder for a Weyl semimetal, if you do power counting, disorder is actually irrelevant. Okay, unlike graphene. Graphene, it's marginal and eventually it's marginally relevant. So a small amount of disorder in graphene ends up giving you a finite density of states. A small amount of disorder, weak disorder for this Weyl semimetal, because it's in 3 dimensions with a smaller density of states, actually doesn't give you a finite density of states. Okay, but transport is slightly more subtle, so I won't really talk much about this. So we looked at a different effect which is more likely to give you a temperature-dependent conductivity, which is the Coulomb interactions. And for a semimetal, like graphene or this Weyl semimetal, it turns out that Coulomb interactions alone can end up giving you finite resistivity. Okay, so usually for a metal, you need a disorder to get a finite resistivity. If you have Galilean invariance, you need something to relax the current. Here, if you apply an electric field, the electrons and holes get accelerated in opposite directions with opposite momentum, and these can collide and relax the current. Okay, so just electron-hole interactions mediated by the Coulomb interaction can end up giving you a relaxation of the current if your chemical potential is at the neutral point. Okay, so you can make a back-of-the-envelope calculation for this effect. Okay, so there's the envelope. So let's make a quick calculation for what would happen. So you have conductivity given by density of states times the diffusion constant. You can estimate the density of states. It goes as the square of the temperature for this particular density of states. The diffusion constant has got a relaxation time appearing. This is like a critical system. It's got no intrinsic scale. So the relaxation rate will be proportional to temperature. Okay, and the coupling constant squared. You can put this all together and you get an estimate for the conductivity. Roughly speaking, it goes linearly with temperature. Okay, like resistivity rises as 1 over temperature. There are some log factors over here coming from the renormalization of the interactions and the velocity. You can do a better job by doing the quantum Boltzmann equation, but all that gives you some factor of order 1. Okay, so you can take this and try to match it with the experiments, let's say in yttrium. So this, I guess the red is the theoretical and this blue is the experimental plot of resistivity as a function of temperature. So we fit our expression to that. And the fit parameters are quite reasonable. Okay, you get reasonable Fermi velocities and fine structure constants and so on. So it may be actually consistent with this sort of picture, but this is a very simple-minded approach to transport. One has to also look at disorder and possible small doping coming from vacancies and so on. Okay, but at least for a start, it looks promising that some of these materials in the Pyrochlore Iridates are Weyl semimetals. Everything is kind of magnetic scattering here. You don't have time reversal symmetry. What do you mean? Do you mean like a so this irrelevance argument actually didn't, I think I know what you're talking about. You're thinking about some protection coming from the fact that it's a hedgehog. So I'm not invoking that at all. So this argument about disorder being irrelevant has, even if you have a disorder that scatters you between the nodes, you need a finite strength of disorder before it becomes relevant. Now over and above that, you can say there's some suppression of backscattering, but usually that's not a big effect, but maybe a factor of 2 or something. It's not a big effect usually. Okay, so these ab initio calculations give you this kind of a phase diagram as you change the Coulomb interactions U. There's another parameter here, the magnetic field. I won't talk about that. And what they tell you is that there's a range of parameters which we believe is actually physical for several of these materials where this Weyl semimetal is being realized. If you increase U, you get a Mott insulator. The fact that you have some tunability in this first element, that helps. Even if you find something that's in the Mott insulator phase, you can find another one that lowers the correlations and may help you get into this Weyl semimetal phase. Okay, so the most striking consequence of finding a material in this phase are the surface states. In this particular case, there are many of these Weyl points, so you get many of these Fermi arcs. But in principle, you should be able to see these kind of Fermi arc surface states and surface experiments, very much like what Zahid was talking about, ARPAS, STM, and so on. And that will be very striking, okay, to see real Fermi arcs on the surface of some material. Okay, so I mainly talked about this Pyrochlore Iridate as a candidate. There are other candidates proposed. In fact, I think it shouldn't be that hard to find a candidate in this phase. There's this double Weyl point that has been proposed to be realized in somewhat more conventional material, mercury chromium selenide spinel, which is a ferromagnet. So there are some initial experiments on that. We don't know yet if this is really happening. There are other nice proposals by Leon Billens and collaborators. You can think of this Weyl semimetal as being something that occurs when a topological insulator is being transformed into a trivial insulator. Okay, but you must break either time reversal or inversion symmetry in this process. So Zahid alluded to this before. If you can tune from one phase to another, you put in magnetic order, you can get a Weyl semimetal. So that's proposed as a being realized in these heterostructures, or you can break inversion symmetry, don't break time reversal in these mercury telluride heterostructures. That's another proposal that's been put forward. This is nice because it has the minimal number of Weyl points. Okay, so let me how much time do I have actually? No time? 5 minutes. Okay. Yeah, so that should be enough for the other half of the talk. So let me tell you about a slightly different setting where everything I've talked about so far is something that can be realized in a correlated system, but in fact to describe such a phase, we can perfectly well describe it by a non-interacting model which has some mean field order parameters. Okay, so it has correlations in reality, but we can kind of, from the theoretical point of view, we can ignore these correlations to make a caricature of the phase. Okay, but what about phases where you cannot do that? Really correlated phases where even the caricature is strongly correlated. Okay, so it's been proposed that in these honeycomb lattice iridates, materials where the iridium forms a honeycomb lattice with these oxygen octahedra, if you look at these materials, they turn out to be Mott insulators. They show Curie-wise magnetic susceptibility. They're insulated with Curie-wise magnetic susceptibility. So you have these J to the half moments arranged on the sides of a honeycomb lattice. Okay, and the question is, how do they interact? If you have spin-a-half moments, we have all of these rules, the Goodenough, Anderson, Kanamori rules that will tell you how to figure out what the magnetic exchange between a pair of moments is. Okay, what happens when you have J equal to half? So there's a very nice piece of work by these people who showed that in addition to Heisenberg exchange, we can also get this very unusual term because of spin-orbit interactions. Okay, the way this term looks, it's ferromagnetic because it's mediated by 90-degree oxygen bonds, but it turns out to be an icing-like term. It only couples one component of the spin, and that particular components change depending on which of these bonds you look at. Along the red, it's X and X. Along the screen, it's YY, and along the blue, it's ZZ, for example. Okay, so this sort of model has been studied before, amazingly by Kitaev, who showed that he could solve this model exactly. If you don't have the Heisenberg term, you can solve this exactly. Okay, so the hope is that if this term is large enough, we might be close enough to this model where the exact solution applies and we might get a quantum spin liquid. Okay, sorry, I should have said the exact solution that Kitaev showed was actually a very unusual phase. It's a spin-disordered phase with many exotic excitations. I think Bhaskar will talk more about that. And it can be shown to be realized exactly in this Hamiltonian. Okay, so this is, of course, an extremely frustrated model because no kind of order appears. And this frustration really appears from spin orbit. Okay, the lattice is not frustrated, it's honeycomb lattice. Okay, so experimentally, unfortunately, it appears this material is not quite in this strongly frustrated limit of just having this term. It actually orders magnetically at some low temperature, but it's fairly frustrated. Okay, the hope is that we have both of these terms, J and JK, and the JK term is significant. Okay, we still need to wait and see whether it's really this JK doing the frustration or some other source of frustration is also present and more important. Okay, but the question we asked is that although it's not a quantum spin liquid, perhaps if I look at doping this system, the phases that appear in doping may be more resistant to the exact values of this J and JK. Okay, so we considered a TJ model on this honeycomb lattice where the magnetic interactions are not just J, but also you have this JK, this Kitaev kind of term. Okay, the question is what kind of conducting states emerge when you dope this kind of Hamiltonian. Okay, so I'll quickly summarize the results. I can tell more about the technique later. We use a slave boson technique, so-called SU2 slave bosons. This is doping, that's temperature. And what you find is that in doping this honeycomb lattice model in the regime when you realize a quantum spin liquid, you get a PX plus IPY superconductor, so it's a topological superconductor. And what's more interesting, it's a spinless P plus IP superconductor. Okay, so it turns out the dispersion of the quasi-particles over here is completely different from the dispersion of electrons on the honeycomb lattice. Okay, whereas at high doping, you get superconductivity again, which is topological, it turns out. But you can understand that superconductivity as having heavily doped honeycomb lattice, and the Fermi surface of that honeycomb lattice gets paired by this ferromagnetic term, into some spin triplet phase. Okay, so there's another parallel work which has similar conclusions. They use a weak coupling analysis rather than the slate bosons, and they also find spin triplet superconductivity. Okay, so I don't have much time, but there are some interesting points over here of this doping system, of this dope system, which arises from the fact that you can actually solve the undoped problem exactly. Okay, so you can make comments, you can make statements about the doped case, which you cannot normally make for in a typical doped magnetic system in 2 dimensions. And one of the things it tells you is that there's some regime of parameters where this slate boson theory can be trusted because it uses the same variables as this exact solution given by Kitaev. Okay, so the question maybe we can talk about that, but let me conclude now since I'm running out of time. So the main point I wanted to convey is that there's new and interesting physics when you combine correlation effects with spin orbit interactions. I gave a couple of examples, this Weyl semimetal, and there's still quite a lot of things to be figured out about this Weyl semimetal, although it's fairly simple to describe. What are the novel transport features? Are the interesting magnetic field effects? So it's known that Weyl fermions have an anomaly, and that translates into should translate into certain effects in this solid. You can ask questions like, are there quantum oscillations from Fermi arcs? What are the candidate materials? And finally, I talked a bit about doping some of these unusual spin orbit Mott insulators, where you get unusual kinds of superconductivity. Okay, let me stop here.
A very quick question. So suppose I take this semimetal and put in a magnetic field in some direction so as to open up a gap. What happens to the surface states, to the arc on the surface?
So magnetic field doesn't open a gap. That's
just think of a Zeeman field. If you have a sigma dot p, would it?
Yeah. So we put on a Zeeman field. So this is think about 3-dimensional Dirac modes. They're extremely stable. So let's say I have a dispersion which is sigma dot p, and you add to it a Zeeman field, I think something like that you're thinking. Yeah, so what this does is it just shifts the Weyl point. So you can ask about the orbital effect. The orbital effect is actually quite interesting, right? So if I have an orbital effect, I have this term. Okay, so what happens then is that you get Landau levels, okay, for the x and y component. But you have a third component which is unaffected by the orbital effect. So if you go to the lowest Landau level, that's the set of states that's polarized with sigma z equal to +1. Right. So there you actually get a chiral mode. You get a mode that if sigma z is 1, the dispersion is just pz. Okay, so it's moving up. And at the opposite y point, it's moving down. So these two states are actually connected via this Fermi arc. So this is another way to see that there has to be a Fermi arc. Because you have a state that's moving up, it can't disappear, it has to come back down. So it goes up to the surface and goes around the surface and comes back down.
Okay, I have a question like how the spectral function would behave at the Weyl point, because we have some spectroscopic level on Weyl equation.
So the density of states is very small. It goes as the square of the energy. So it may be hard to tell from an insulator actually. You'll have to be able to track this density of states going to 0 as the square.
You see some weak intensity at the Fermi level in Y to R2 or something.
I see.
It behaves like simple fermions, like the dependence. So, but is it can be called Weyl prompt particles or?
Well, we have to talk about it. This is angle integrated. So then you have to just look for this density of states. It's a bit like topological insulator with a single node. But if you have this kind of a surface state, then you can get scattering between the different arcs, and that will show up in the QPIs.
So let's. Sorry, I just wanted to follow up on the question of this gentleman to my right about spin flip scattering. So you pointed out rightly that scattering between the nodes by itself doesn't kill you, but presumably spin flip scattering comes from impurities that have memory, and so one also has to think about condo aspects.
Right.
Now, people have thought before about these soft gap condo problems where the density of states goes like a power law away from the Fermi level. And as I remember, a power law of 2 was actually the critical one. I wondered if people had looked into the properties of condo impurities in...
I would expect that for graphene, you need a finite interaction strength before you get the condo effect. Here, the density of states is even smaller. It goes as a square of the energy, so you would need a very large interaction strength to get the condo effect.
Okay. Good. Thanks. I think we're already running a bit late, so let's thank